Okay, so today we have Radoslaw Kycia speaking about Poincare lemma and applications to physics. So the floor is yours. Feel free to introduce yourself to maybe if someone doesn't know.
Okay,
So, yeah.
thanks for the introduction. I'm Radoslaw Kycia from Masaryk University. I'm a PhD student at Mathematical Faculty, Institute of Mathematics and Statistics, and I will be talking about Poincare lemma and applications to physics. Well, the Poincare lemma is very old subject, like since the Poincare it's say more or less known. But I will present it in such a way that I think it will be interesting for physicists too. Well, I hope physicists use it, but maybe not in such a way which I present. Okay, so let's maybe start. The outline of the talk is here. First I will remind you the Poincare lemma, and then I will associate it with something which is called Bittner operator calculus. It's after the Richard Bittner. It's some, I think, Polish mathematician, but this idea is not well known. But I think it's very essential in understanding of creation and annihilation operators. So maybe I will stop a bit and explain it better. And then I will use this operator calculus and Poincare lemma to define something which resembles fermionic harmonic oscillator. You will see that the structure is more or less the same. And I have also some subject about complex manifolds and Poincare lemma on these manifolds, but it's very technical, so maybe I will go through this very fast. You can always stop me if something will be interesting. And then I will switch to Riemannian manifold, where you have metric and you have Hochstar. And if you have Hochstar, then you can also have codifferential. And if you have codifferential, then you can try to formulate Poincare lemma for codifferentials. So that will be the second part to define analogous definitions as for general Poincare lemma. And then because most equations of physics have differentials and codifferentials as these differential operators inside, then if we know how Poincare lemma is defined for differentials and codifferentials, then we can solve equations of mathematical physics, mostly all of them, like Dirac equations, Maxwell equations, some equations from string theory, and at the end, I will present a homotopic version of fermionic oscillator. I mean the version for codifferential, not for differential. And I will at the end show the bibliography, which are three points. Okay, so let's start from Poincare lemma. Okay, so here is this mathematical version of Poincare lemma. It's, I think, the most advanced version. Cohomology group of dimension n over the k-dimensional Euclidean space is the same as the cohomology group of the point, which is exactly R for n equals 0 and 0 for n for n greater than 0. It means that you can shrink the space to the one point more or less, and this dimension of this hk can be understood as a number of closed K-forms. So closed means in the kernel of exterior derivative, so d omega is equal to 0, that are not exact in the sense that they cannot be represented as some other differentials of some lower degree or lower grade forms. So omega is not alpha. So if this hk vanishes, as here, then every closed form, so every form which is in the kernel of exterior derivative, is of the form d alpha, where alpha is 1 degree less. Okay, and the more say or less advanced version of this is that if U is some star-shaped open subset of some Rn or manifold, then every closed covector field or form on U is exact, which is exactly that Hn is of this U is Hn of the point. But it's not quite useful in computations. For example, you don't have a proper formula for inverse exterior derivative, and that's what we need in applications in physics. So
Maybe, Radek,
yes,
maybe you should point out why there is this difference between n equals 0 and n bigger than 0.
yeah. The Euclidean space is in one piece, so it's simply connected. So here is this R is for simply connected, so in one piece, more or less. And yeah. So,
Yeah, well, I guess what I wanted to you to say is that that it's impossible to have -1 forms.
yeah,
Uh,
yeah, it's yeah.
so if you have a
Good point.
closed form, 0 form, then it cannot be exact.
Mhm.
And I guess this exception is missing from the second version you have of Poincare lemma,
Uh,
the 0 forms.
well, it's not written exactly, but the idea is the same because in the definitions of these covectors or forms, you don't have -1 forms. So as you said, it also works here. But it's
Yeah, but why? So is it because you secretly are assuming that they have compact support or something like that?
no, it's only that you start from functions and you can generate the higher degree grade forms by acting with exterior derivative. More or less.
But why don't you have? I mean, so the point is in the first formulation you have on this page, then the 0 forms, constant 0 forms are not exact, of course. But and that give you this R. But in the second version, it seems like it's not mentioned. So it seems like that every closed form or covector is okay. Your only covector is a one form.
Yeah, exactly.
Okay.
It's like more for physicists version because I usually
So it's only for n equal 1.
no, it's general because this
It
star-shaped region has the same properties as it's locally this RK. So
I mean k equal 1. Well, actually, I guess it's a little bit confusing. Yeah. So n and k switch in your two definitions.
sorry, yeah,
Yeah.
exactly.
So I mean it's only for one forms for so k equal 1 in well
No,
n
no,
n
no,
n, n equal 1 in the first definition.
no. You can have k arbitrary. So n varies from 0 to k because higher. So if n is greater than k, then these cohomology groups are automatically 0. So
Sure, but in the second formulation, it's only for n equal 1.
no,
You
no.
mean because of the word covector?
Yes.
Okay, yeah. Sorry. What I meant is that if you replace this covector by differential form, then it works for all n.
Good.
Mhm. It's a good point. Yes. Sorry, I didn't notice it. Okay. We need something more practical in calculations. So we define something which is called a homotopy operator, which is this large G operator which acts on some differential form, and it is defined as integral from 0 to 1 of omega, in which we insert this dt vector. And what does it mean? It means that we extend. So we have manifold M and differential forms on this manifold, and we extend this omega by one dimension, and this is the t coordinate here, and this G fulfills the very nice property which is called homotopy invariance formula, which will appear many times in this talk, and it means that dg plus gd is equal to this is insertion of this manifold M inside the M times R manifold. So this is exactly it of at acting on X is Tx. So you insert at T this point X. So this I1 and I0 stars are pullbacks of differential form, which is defined on M times R along this insertion. So you say pull back this the differential form to this M manifold from M times L manifold. Okay, this is very general formula, and it's proved almost in every, say, less or more advanced book in differential geometry. And this formula is very useful because you can choose some kind of homotopy. So homotopy is a continuous map which maps from interval 0, 1 times n to m. It's some kind of, say, shrinking of loop or extending it if you want to visualize it. So, but generally, this is a mapping between some map f from m to n to g from m to n, which is parameterized by some kind of time from 0 to 1. So, for example, f of 0 is f and small f, and large f of 1 is g. And if this time is between 0 and 1, then there is something between f and g. And then if you select some kind of homotopy f, then you can define a homotopy operator which is fixed on this specific form of homotopy, which is defined as g composed with pullback of f. And using this and this homotopy invariance formula for the specific homotopy, we have homotopy for invariance formula for this f, which is hd plus dh acting on omega is exactly this. And if you use this the right hand side of this third formula, then you have pullback along g minus pullback along f, and it's quite easy to see. So generally we have this homotopy invariance formula for h tilde homotopy operator, but it's also not useful in computations because we have to fix this homotopy first. And it occurs that the very useful choice for this homotopy is linear homotopy. So if you are on the manifold, you select some star-shaped region, and then it's diffeomorphic with Rn or some open subset in Rn, and you select some say central point like x0. And you have from x homotopy to x0, which is parameterized by this time t. So if you change t from 0 to 1, then you move from x0 to some point x along the ray. More or less, that's why you need this star-shaped region. And in this homotopy, g of x is x, so it's identity map, and f of x is x0, so it's constant map. And if you use this this G definition and well, this H definition, which is G composed with specific homotopy, this linear homotopy, then if you manipulate a bit, then you get this formula for H, which is this integral from 0 to 1, and you take k vector, which is this x minus x0 dA, inserted to this omega, but this omega is evaluated at the point in this homotopy ftx, and here is t to the power k minus 1, and it is integrated over d. It's, well, maybe it's not well-known formula, but you can easily get it from this previous formula. So you take form, you evaluate it at the point which is distinguished by this homotopy, and you insert this k and integrate over it, and that's how you get this h omega. And for this homotopy, you get this homotopy invariance formula dh plus hd is identity because this g is identity, and here is pullback along the constant map because f is constant map. So this term works only for or it's not zero for only for zero forms. So it's evaluation of the function at x0 for zero forms. So for the functions, but for higher degree forms, it's zero. It's nullify all higher than.
Radek, may I have a question?
Yeah, sure.
So actually, what does the homotopy operator compute for us, or what's the purpose of?
Yeah, that's the good point. I will go to this now. Okay, maybe let's see it here. So if you have a closed form or in star-shaped region you have closed equal to exact, then this d acting on form is 0. So this term hd is 0. Okay, and so what is left is dh acting on form is identity, and if this form is not 0 form, then this x0 pullback is 0. So you have dh is equal to identity.
I see. So
So
it provides the inverse, yeah?
Yeah, exactly. This h is local inverse of this exterior derivative.
I see. Thank you.
That's what we need in solving equations. Inverse of exterior derivative. Yeah.
One of these d's, I'm sorry, one of these d's is, they're not the same d's, right?
Yeah,
one of them is like,
exactly.
okay.
Mm-hmm. Yeah, one acts on different, so
yeah.
this d acts on some forms, and this d acts on 1 degree lower forms.
So should I think of, if I have my forms on m times r, and I write the whole chain, and I have the other chain with just forms on m, this h really gives me quasi-isomorphism, right, of these chains? Is that
Yes,
the thing?
we will come to this later. I will present the full diagram for this.
Okay,
what you mean.
cool, thanks.
But it's a good question. Yes. Okay,
Sorry,
so we have this.
back.
Yeah. Sure.
Just a bit back, a slide back.
Yeah, sure.
But isn't as I mean the lowest line as x0 and x equals x?
What was it again?
I mean, you said that as x0 is the constant map.
Yeah, it's pulled back along the constant map because it's pulled back along this fx equal x0.
Okay.
Yeah, so for zero forms, like for functions, it evaluates this function at x0. But if you pull back the 1 degree form or high degree forms, then it pull back along the constant map is 0. So it is 0 for n greater than 0.
Okay.
Hmm? Okay, so we have this h, which is defined here. And it has very nice property. So h square is equal to 0. So it's the same as for exterior derivative. And it's a bit longer proof, but you have to believe me that this h distinguish some special part, some special some module in the exterior module. It's called anti-exact forms. The elements of this module are called anti-exact forms, and they are defined as the so omega is anti-exact if it's of the form h acting on alpha, where alpha is some kind of form. So it's something like exact form, but with h instead of d. But you can also characterize this anti-exact form by different properties. Like if you insert this k vector inside this anti-exact form, then it's 0, and it also if you evaluate it at the center x0, then it's 0, because this k inside. What is this? Oh, it's here. Because this k inside has this x minus x0, and it's inserted in omega. So if you evaluate this formula at x0, then you get 0 under the integral sign. So it's 0. Okay, so they are defined locally, but still we'll see that they are useful. So this is the second characteristic, and the third characteristic is that you can treat this hd plus dh equal to identity. You can forget about this pullback along the constant map for the functions because it's non-zero for the function. So this hd plus dh equal identity is something like projection operators. Hd is one projection and the dh is second projection. So you can distinguish this anti-exact form as a forms which results from acting of hd on arbitrary form. So it's projection of arbitrary form along this hd to the anti-exact forms. So there are some characteristics of this module of anti-exact forms. And what is very interesting is that locally in star-shaped region, you have Dirac sum decomposition. You have to prove it, but you have Dirac sum decomposition of k forms into the exact forms plus anti-exact forms. So locally you have some kind of vector space. In one direction is exact and the second direction is anti-exact forms. Okay, so now we go to these questions about how it looks like. So here is this plot of this decomposition. So you start from the bottom, and you have functions. So all functions are anti-exact forms, and the h acting on this anti-exact form is 0, because anti-exact form can be also defined as a kernel of h, this homotopy operator. And you also have this kernel of d, which are constant functions. I denoted them by R here. And if you go here along this d differentiating functions, you get exact forms, which is and you can go back by homotopy operator, and you get this anti-exact forms. And yes, so this is the first level. The second level is you start from anti-exact 1 forms, and if you differentiate them, then you get anti-exact 2 forms. And you can go back by homotopy operator to this A1. And also, of course, A1 is in the kernel of H, and A2 is in the kernel of D, and so on, up to the volume form, which is on the top. And the volume form is exact because D acting on volume form is 0. Yeah, so it's in the kernel, but you can go back to the n-1 anti-exact form of degree n-1 by homotopy operator. So that's the full decomposition. And as someone asked me, these H and D are different because they act on between different spaces, but usually they are denoted by the same symbol. Okay. We can, because each of these HD action is like splitted somehow, so we can select one of this piece. And we have this AK, which is transformed into AK -1 by H, and in the opposite direction by D. Okay, and we will try to find proper interpretation in physical terms for this diagram. But before that, I have to say something about Bittner operator calculus. And it's very nice idea to restore in operator terms these properties. So we have 2 operators, derivative and integral. So derivative of integral is the function, so it's some kind of identity operation. So derivative acting on integral is identity. But here, if you have integral acting on derivative, then it's identity minus projection on the boundary, which is f of q, because q is lower limit of this integral. So it is almost identity up to this boundary projection. And Bittner extend this notion to general derivative and integral operator. So you have 2 linear spaces L0 and L1, and you define abstract derivative, which is surjective mapping S, which is mapping between L1 and L0, and the elements of kernel of this linear operator S are called constants. In this say normal definition, they are real numbers or constant functions, but generally it can be something different when this S is defined in more abstract or more different way. And you can also define by selecting some kind of this constant from the kernel of S, integral TQ, which acts in the reverse direction, and they fulfill this condition. S acting on TQ is equal to I, and TQ acting on S is equal to I. Identity minus this projection on the boundary, which depends on Q, because here integral depends on this lower boundary. Yeah, so this Q is constant, which is kernel of normal derivative. So here is the generalization of this. And note that we don't assume that this S, which is abstract derivative, fulfills Leibniz rule. So it's even more general than usual derivative, because we don't assume that it fulfills the Leibniz rule. Okay, so that's the idea. So we have 3 operators: derivative, integral, and projection on the boundary conditions. And they are say abstraction of this formula on the top of the slides. Okay, so let's go back to our homotopy operator. So we have the diagram as here, and okay, so we restore Bittner operator calculus, because if you look on this AK and AK minus 1, then we have D acting on H is equal to identity, because we go from AK to AK to EK, and then go back by H. So it's identity. But from homotopy invariance formula, we have HD is identity minus projection on the boundary condition. Okay, and we also note that D square is equal to 0 and H square is equal to 0, and probably this nilpotency suggests that there can be something interesting, because in quantum mechanics we also have a similar behavior for fermion system. I mean this Pauli exclusion principle. Okay, so let's go to fermionic harmonic oscillator. So I will try to formulate this quantum harmonic oscillator for fermions in terms of this homotopy operator and exterior derivative. So just for a reminder, you are physicists, but
Radek,
yes?
can you just remind me? It was the nilpotency. Was that an assumption in the Bittner? Or was
no. It's additional assumption. So Bittner operator calculus is general notion of these properties in 10, but you can add some additional constraints for these operators, because, for example, for this S you don't have Leibniz rule, but you can add it and you have more restricted this operator calculus. And also nilpotency is not assumed here, but if you assume, then you restrict this operator calculus to the operators which are nilpotent. It's something additional. Okay, so but it's a good question, because it's something new, so it's worth to ask, just to be on the safe side. Okay, so fermionic harmonic oscillator is so we have two operators, A and A dagger, which are called creation annihilation operators, and Hamiltonian of the system is defined as here. And these operators, creation annihilation, fulfills anti-commutator relations, which are probably well known by you. And there is matrix realization for these operators, which is here. So A is like a rising operator, and A dagger is lowering operator. But we have similar behavior for D and H. So DD is equal to 0, which is the same as this anti-commutator of AA, because it's 2A and it's equal to 0. So AA is equal to 0. And HH is 0, which is the same as this creation operator relations. And from homotopy invariance formula, we have HD plus DH is equal to identity and minus this pullback, but only for but this pullback is 0 for non-functions like 1 or higher degree forms. So for higher degree forms than 0, this pullback is 0. So we have HD plus DH is equal to identity, and it's exactly this commutation relation. A dagger is equal to identity. Okay, so we can define Hamiltonian for this homotopy and exterior derivative operator, which is HD minus DH, and we can try to solve eigenvalue problem. So we solve harmonic operator, harmonic oscillator problem, but for this homotopy like setup. Okay, so for k between 0 and n, we have eigenvalue -1. And for this eigenvalue, HD omega is equal to 0. And that means that omega is in the kernel of this projection operator HD, which gives that omega is exact form. So lambda -1 distinguish exact forms. And okay, so for lambda not equal to -1, we have HD omega. Omega is general form, but HD is projection operator. So HD omega belongs to this anti-exact form. So omega also depends to this anti-exact form, and therefore HD omega is omega. So this is omega is anti-exact. So solution of this equation is only for lambda equal 1. So lambda equal 1 corresponds to anti-exact form. So we have two eigenvalues, plus 1 minus 1, and each of these eigenvalues corresponds to exact or anti-exact forms. For k equals 0, we have lambda equal 1, then f is arbitrary element of functions which are anti-exact forms. And lambda not equal 1, if you substitute not equal 1 here, then you get that f is equal to 0. And for the top forms, you have that eigenvalue is minus 1, and then this, say, volume or proportional to volume element form is exact. And there is no eigenvalue with minus 1, no other eigenvalue, because then mu is equal to 0. Okay, but in quantum mechanics, this A dagger is defined as an adjoint, so you have to have some kind of product in Hilbert space. And here you don't have product. You only match these operators H and B by commutation relations. So this Hilbert space is missing here, but the spectrum looks more or less the same or behaves the same as for harmonic oscillator. Okay, so now a fast detour into complex manifolds. Okay, so complex manifolds are even-dimensional manifolds which have this complex structure, which is J operator, which squares to minus identity. And this J splits tangent space into two parts, TPM plus and TPM minus. And the splitting is in local setup is into holonomic part, which is spanned by d over dz mu, which is this in terms of xy, and anti-holonomic part, which is d over dz bar. Okay, and dualize this notion, you have split of one forms into omega 1 0 and omega 0 1, which is spanned by dz and dz bar. And you also have exterior derivatives, which acts for dz and this dz bar, which, for example, they are called Dolbeault operators. And the first one increase the first index by 1, so from p to p plus 1, and is defined locally as dz wedge the derivative with respect to z. And the second one is increase this q by 1, and it's defined by dz bar multiplied by this derivative. And the full derivative, if you look on this formula here, it's exactly the sum of these two locally, of course. And from this d square equals 0, if you substitute for this nabla plus nabla bar, then you get d square equals 0, d bar square equals 0, and this commutation or anti-commutation relations. Okay, so I think it's more or less known here, but you can also do the similar thing for this homotopy operator. So to do it, you have to look on this k vector, which is x minus x0 and y minus y0 times the base, and and homotopy operator is as follows. So it's exactly the same as in previous case, but you have x and y coordinates, which are two couple of coordinates. So you split this k of vector into k plus and k minus, where k plus is z minus z0 mu dz mu, and k minus is complex conjugate of this k plus. Okay, and then you can define the homotopy operator, which is say sum of h plus and h minus, where this h plus decrease this first index of the form, or degree of the form, and the h minus decrease the second or anti-holonomic index of this form. And h plus minus is defined as insertion of this k plus minus inside the omega evaluated at homotopy times dk minus 1. It's an analogy of the previous formula, but for the complex state. And you, from this formula h square equals 0, you also have that h plus square and h minus square is equal to 0. And h plus h minus plus h minus h plus is equal to 0. But this homotopy invariance formula cannot be split in two or more relations. It's more complicated. So So this homotopy invariance formula, if you insert all these operators, you get very complicated formula. There is no visible pattern for some kind of scheme. But you can draw it, and it has very nice structure on this graph. So from each node, there is H, which acts diagonally, and D, which acts also diagonally, but in the reverse direction. But if you want to move up or left, right, then you move along the H plus or H minus and D or D bar. So it's some kind of like the composition of movement across the diagonal into movement up and left or down and right, something like this. But everything what I said is local notion. So first you select some star-shaped region, and then you define homotopy operator, and then you have this complex. And also you can notice that this H plus and H minus or H is inverse of exterior derivatives. So we have something like reversed Dolbeault complex for H plus and H minus. Okay, but there is also very nice, okay, what I want to say that there is some kind of boundary complex which has this Q equal to 0, and this complex, if you use only this D or nabla and H plus, then it fulfills this homotopy invariance formula. So on the bottom you have this Dolbeault complex, which is say only complex for Q equals 0, and on the right you also have this say part of the Dolbeault complex, which is subcomplex of the full complex, which is for Q equal to 0, or so P equal to 0, and it consists D bar and H minus, and it also fulfills this homotopy invariance formula. So generally you cannot split this H plus and H minus into subcomplexes, but you can do it on the top and on the left. Yes, so yeah, on the left. So, okay, so now let's go to Riemannian case. We have Riemannian manifold, so manifold and the metric G, and this metric induce Hodge star. So Hodge star is mapping from R forms to N minus R forms, and it's say some kind of idempotent. No, sorry. So star is proportional to its inverse. So if you act twice using star, then you have some up to factor, you get the same form. And so you can define inverse of this star operator by this formula. Here sig of G is signature of the metric, which is determinant over modulus of the determinant, and eta here is the sign of this grading of the form. So if form is P form, then this eta acting on omega is -1 to P omega. So star to -1 is defined as a star, but with some coefficients. And using this, we can define a codifferential, which is first you act by eta, then star, then D, and then star to -1. It's general. It's defined invariant because it doesn't contain some reference to coordinates. Okay, and then now you have Poincare lemma for codifferential. Mathematical students get it usually as some kind of exercise because the proof is by use the original Poincare lemma. So this Poincare lemma for codifferential is as follows. So for star-shaped region U, if omega is co-closed, so codifferential acting on omega is 0, then there exists alpha, which is 1 degree higher form, such that omega is delta alpha. And here is the proof if someone wants, but I don't go through this because I leave it as an exercise. Okay? But still, we don't know what is inverse of this delta. We only have that this inverse exists locally in star-shaped region, but we don't have any formula for inversing this delta. Okay, so we have to define some kind of homotopy operator. And if you think a bit, then this inversion or this homotopy for codifferential is defined as follows. So h, small h is a star. So first you act by star, then you act by homotopy operator, then by star to -1, and then you multiply by this -1 to the grade of the form. And as someone asked at the beginning, H is not a single operator, it's a chain of the operators. Each operator acts from lambda r to lambda r -1, and it's defined by this formula, where here eta is -1 to r plus 1. And here is drawn as it looks like. So we jump from, say, lambda r to lambda r plus 1 by h, and in reverse direction by delta, and the same is for b and h, large h. So we have like two mirror structures which behaves the same, but the arrows are reversed. Okay, and if you use original homotopy invariance formula, then you can also prove that the same formula or similar formula works for this delta and h, which is this delta h plus h delta is identity minus large s. And this large S is like Hodge dualized version of this pullback along the constant map, which is star hs x0 star to -1. And this large S form is non-zero only for top forms, because this small s0 was non-zero only for functions. So dualizing by Hodge star means that only top forms are non-zero. So some kind of volume forms or something which is proportional to volume forms is non-zero for this S x0. And this H and delta have similar properties to this large H and B. So H square is 0, delta H delta is delta, H delta H is H, and so on. And we can also define coexact forms, which are normally defined like a kernel of this codifferential, but we can also define anti-coexact form, which are dualized version of this anti-exact form, which are image of this H delta operator, which can be treated by this homotopy invariance formula as a projection. So if S of X is 0, which is 0 for non-top forms, then delta H plus H delta equal identity can be treated as projection. So you split the whole vector space of the forms to the delta H part and H delta part. And anti-coexact form can be defined as one of these projections, so H delta projection. Alternatively, you can define these forms as so you take a form and you wedge it with k vector, which is bimetric dualized to the form. And this works because we have this formula. So if you insert the vector, which is say dual version of the form, inside the star phi, where phi is formed, then it's the same as star phi wedge alpha. And this wedge here is exactly this wedge here. You have to compute it, but that's the rough idea how it works. And also because this k consists the term x minus x0, then omega acting on x, omega at x0 should be 0. And this defines completely this anti-coexact forms. Okay, so why these forms are interesting? Because you can prove that the whole vector space of the forms on the manifold, so on all cotangent space or tensor product of exterior product of cotangent space can be splitted as a direct sum into say 4 parts. So here A denotes exact, A denotes anti-exact, C coexact, and Y denotes anti-coexact. So you have these 4 parts. It results from the fact that the whole vector space of these forms can be split into exact and anti-exact part as a direct sum, and also into coexact and anti-coexact part. So if you compose these 4 splittings, then you get these overlapping 4 parts. Okay, so if you know this, then you can start to do some physics. Okay, and now we go to applications of this formula. So everything works very nicely when you define something which is called Clifford module. So it's some kind of say Clifford algebra put it on the manifold and formulated in terms of the differential forms. So we have Riemannian manifold with some metric G, and this Clifford bundle can be very easily defined in terms of exterior differential forms on the manifold with multiplication by, so we have vector v from the tangent space at some point x, and some differential form psi at the same point. And then you define the Clifford multiplication of the vector by the form by this formula. So you take the wedge of this vector times psi. Of course, this here we had to dualize form to the vector, sorry, vector to the form, and insert this vector inside the form. So this multiplication increase degree of the form and lower degree by one of the form. And using this, you can define exterior derivative because if you have a metric on Riemannian manifold, you have also Levi-Civita connection. And if you have Levi-Civita connection, you can define exterior derivative by this formula and codifferential by this formula. So in these terms, you can define Dirac operator, which is in this setup called the Dirac color operator because it's general Clifford bundle, not spinor bundle, which is ideal inside this Clifford bundle by this formula. So D is equal to contraction of AI with exterior derivative along the direction AI, which is by this formula 42 D equal D minus delta. So it's also well-known stuff. But now you can try to define.
Sorry, why do you need current derivative? I thought it's just forms, so you can just have exterior derivative and the dual. No?
Once again, because there's some.
The D, why do you use the nabla there? Why can it be just normal exterior derivative there? Because it's just acting on forms, no?
Well, so if you have this Riemannian setup, then okay, yeah, you can use here exterior derivative, but you can write this exterior derivative as the wedge product of this vector, because it results from the fact that the Levi-Civita connection is symmetric in, say, lower degrees or lower indices.
Yeah, I know. I just thought that it has some particular meaning. I mean, no question that you can write it like that. I mean,
yeah,
you just don't need it.
Yeah, you only extract from covariant derivative this differential part. That's
okay.
The business. Yeah, but this codifferential is more trickier, but it can be also defined as this.
Even that, you just need Hodge star, right? An exterior derivative. There's no.
Yeah, it is somewhere inside. Yeah, if you expand it and use this Hodge star properties, then it's the same. Yeah, but you need metric structure. Yeah, I agree.
Actually, Radek, you don't. You only need a volume form.
Sorry?
No, you need conformal structure.
Yeah.
You need volume form in 2D. But in otherwise you need full conformal structure, right?
Yeah, it's very good discussion because the Hodge star can be defined for so if you have even dimensional manifold, then if you have half the dimension, then you need only conformal structure. But if you consider the Hodge star on the form 1 form, 2 form, and so on, you need the full metric. So it is very easily visible when you consider the Maxwell equations, because this stress tensor F is 2 form, so it's half of the dimension of 4. So full Minkowski space has 4 dimension, is 4-dimensional, and metric tensor, and this F tensor is 2-dimensional, and you need to define, and that's why these Maxwell equations are conformally invariant. But if F would be say 1 form or 3 form, then there will be no conformal invariance. So full metric would be needed. But for Maxwell equations, because F is 2 form, you need only conformal structure. So the symmetric group is bigger by this conformal invariant. Sorry, it's conformal scaling. it's very tricky, but it's good. Very good question. Yeah. Okay, so let's go to the Dirac equation. So Dirac equation in this Clifford bundle setup is as follows. It's vacuum Dirac equation without mass and so on. So it's D acting on C is equal to 0. And we can use this local decomposition into exact, anti-exact, and so on forms to solve it. So how to do it? So take alpha equal lambda k to -1 and beta equal lambda k plus 1, and assume that psi is of this form as the sum of these two. Then if you substitute this psi inside this d acting on psi, and I will remind you that d is small d minus codifferential, then this equation splits. If you look on each degree, then this equation splits into codifferential acting on alpha is 0, so alpha is is coexact. Then you have this say cross term in the middle, and at the bottom or top you have b acting on beta is 0, so beta is exact because we use local approach in star-shaped region, so closed is exact. So it looks like as on this picture. So at the level k-1 you have alpha plus this gauge, but this gauge vanishes because here we have you can scale this alpha or add to alpha some exact form and it vanishes in this middle equation. So alpha is taken by d to say this region in k degree forms, and beta from k plus 1 forms is taken by delta to this also. And this middle equation is the fact that this alpha image of alpha by d is the same as the image of beta by delta, and this is some kind of constraint only. Yeah. As you see, Dirac equations involves 3 degrees which are neighbors. So k plus -1, k and k plus 1. And it's only some kind of constraint for this mapping d and delta, more or less. Yeah. So it's very nice, say, picture about of these solutions of Dirac equation. And we can also do the same trick with Maxwell equations. But first we have to write it as a Dirac-like equations. So generally we have this formula for Dirac Maxwell equation. So D acting on F is 0, which means that F is closed, and codifferential acting on F is some kind of current, which is one form. And you can use, because here is D, here is delta, you can subtract these two equations, and you get Dirac operator acting on F is equal to -J. So this Clifford bundle stuff compress this equation into one equation. It's very nice because in vector calculus you start from 4 equations, Maxwell equations, then using forms you have 2 equations, and then if you switch to Clifford bundles you get only 1 equation, which is Dirac-like, I would say. Yeah, it's very amazing that switch to different notion gives you from few equations only 1, which is very compressed. But anyway, let's start to solve it. So as before, we can split F into two pieces, psi and gamma, where psi is alpha plus beta, and we assume that psi is a vacuum solution of the Dirac equation. So this psi is some kind of like say vacuum, this is some kind of vacuum, say, and if you have this, and alpha is co-closed form, and beta is exact 3 form, and gamma is here is 2 form, because it must be some kind of form. Okay, and using this, because d psi is equal to 0, so from if you substitute this F inside this equation, you get that d gamma is -J. Which means that d small d gamma is equal to 0, and delta gamma is equal to J. And because you have equation d acting on some form is 0 and delta acting on some form is J, you can use these homotopy operators to inverse these two locally and get some solution. Yeah, so that's more or less how to solve this equation. Okay, So now Kalb-Ramond equations, they are used in string theory. The ends of the string have some kind of say charge, and they emanate to these de Bruyn's some current, and these equations are say equations for description of this phenomena. Generally, it's called P-form electrodynamics. So instead of using 2 form for F, you use arbitrary degree form. So you pick, for example, 3 form and consider it in multi-dimensional space, and formulate some kind of Maxwell-like equations for this non-2 form, non-2 degree forms. So you have some, say, K form. In this basic setup of Kalb-Ramond, you have K, which is 3 form, and J, which is some kind of current, is 2 form. And the equations are similar to the Maxwell equations. And if you notice that you can, subtract these 2 equations, you also have Dirac equation, D acting on, where D is this Dirac operator acting on K is equal to minus J. And you can also solve it, assuming that K is psi plus gamma, and this psi is solution of the vacuum Dirac, of course locally, vacuum Dirac equation. And then this delta acting on gamma is J. And then because we have in local inverse of delta, you can act on this and get the solution for gamma. Yeah, and from the previous considerations, we have also solution of this vacuum equation. So we have full solution, which is constructed from these 2 pieces. And I underline that it's only local because we use homotopy operator, which is defined only locally. But it is something. It's we have some solution. It's local, but it's solution. So we are happy. At least I think we are happy for this. And we can also couple this Kalb-Ramond stuff with Maxwell equations. So now this say stress tensor has 2 components: F, which is normal Maxwell stress tensor, and B is this what I called K here. So it's some kind of 3 form stress tensor. Or sorry, so here is 2 form anti-exact tensor. And we can write this Kalb-Ramond's Maxwell system from string theory as this system. So Dirac operator acting on R is equal to K minus J, and Dirac operator acting on K is equal to minus J, which is J is normal current as in Maxwell equations, and J is this K current here from this Kalb-Ramond equations. And we can also solve this system using this homotopy, co-homotopy business, of course, locally in Starship. Okay, so that's if you know how to solve Dirac operator using this local approach and homotopy, co-homotopy operators, then you can solve almost every say classical physics equations where Dirac operator appears, but mostly in every say basic theory of physics, Dirac operator appears, or square of this Dirac operator appears. So you can solve almost everything locally. Yeah, so that's the power of this method. Okay, and the final example is this co-homotopic fermionic oscillator. So instead of large H and exterior derivative, we use small h and codifferential. Yeah, Hamiltonian is the same. We can define eigenvalue problem, which is Hamiltonian acting on forms is eigenvalue of times the forms, and the solutions are the same. So lambda is equal plus minus 1 as for fermionic case, and eigenvectors are exact and anti-coexact forms. So it's dual case to the previous one. Okay, so let's summarize. So as we have seen, the Poincare lemma and resulting homotopy operators have very nice operator properties, especially in this term of Bittner operator calculus, which treats differential as derivative and homotopy operator as some kind of integral. These operators can be used to formulate abstract differential equations. I didn't say much about this, but in Bittner works, he used this notion of abstract integral and abstract derivative to define differential equations in terms of abstract derivatives and to solve it. And he also defined abstract Taylor series and so on. So almost the whole part of the calculus can be reformatted in terms of functional analysis and this integral differential operators. And on Riemannian manifolds, similar structure is induced by Hochstar because it exists when you have metric. And local solutions of many equations of mathematical physics can be better understood, I hope, I showed it here, by exact, co-exact, anti-exact, anti-co-exact decomposition. Yes, as we see in case of Dirac operator. And well, this is maybe more philosophical. So the Poincare lemma is a local result. It works only in star-shaped region of manifold. But we can ask if, because most of us are physicists, if we require from physical solutions to be always defined globally, or only local solution is sufficient for us. So because you know, if you solve some equation, you don't solve it for the whole universe at once. You restrict yourself to some local region and assume that the field vanish outside of the so support of your solution is finite, and you assume that outside of the support the field is zero and solve locally. So do we need the global solutions? Sometimes topological considerations require global solutions, but not always. Okay. Anyway, here are my sponsors, and the papers which or resources which I encourage you to read if you are interested in this subject. The first one is the very nice book by Edelen. He works locally, so everything is in coordinates, and he defined this homotopy operator and derived this anti-exact, not anti-exact, but yes, anti-exact forms, and use it to solve Maxwell equations in closed form. So it's a very nice book. I think it's forgotten, but I recommend it anyway. And the second one is my paper about Poincare lemma and this anti-coexact form and this harmonic oscillator and other stuff. And the third draft, which I try to publish, is about this codifferential and Poincare lemma. It also contains this description of the solution of the Dirac operator, which I mentioned at the end of this talk, and also Riemann potential and Maxwell equations. So the whole structure of these physical theories is explained in terms of differential, codifferential, and homotopy operators. So if you are interested, then I recommend it to you. And also, of course, you can find in these papers on drafts more references for more advanced, I would say, papers. Okay, so thanks for your attention. I don't know, because I have some backup. We have some time, or should I stop now?
We do have some time for discussion. So do you want to talk more about something, or do you want to open up a discussion?
Well, maybe what I have at the end. So I have connection.
Yeah, sure, continue. Yeah.
Well,
I mean, if someone wants to leave, they can leave. So.
Okay. Okay, so what I wanted to say are two slides about connection between Maurer-Cartan form and Poincare lemma, because they are it's very nice connection. So if you have some form omega, then omega is called Dolbeault derivative. If you have some map F from manifold to the group, and then this omega is pullback of Maurer-Cartan form, which is denoted here omega G along this F. So omega is called the Dolbeault derivative when it's pullback of Maurer-Cartan form, more or less, for some Lie group G. And now what is interesting is that there are two equivalent conditions for say existence of this Dolbeault derivative. So omega is Dolbeault derivative for some map, then when it fulfills these two conditions. So local condition is that omega is also has zero curvature, or is some kind of, say, Maurer-Cartan form or pullback Maurer-Cartan form. And global conditions means that the monodromy representation, which is mapping from first fundamental group centered at point B to the group G, is trivial. where this map is as follows. So we take a loop from this first fundamental group, and we map it to the end of this loop in G. Okay, and this tilde is defined as follows. So this loop pullback, this omega, and it should be equal to pullback of Markov form along this lambda tilde. So here is definition of this lambda tilde. So it is defined as the pullback of Markov form in such a way that it's equal to omega pullback along this loop lambda. And if these two conditions are satisfied, then it means that omega is Darboux derivative for some map F. And this Darboux derivative is non-unique. It means that the non-uniqueness means that this F is defined up to left translation by some element of G. It's the same as in integral. So if you have derivative of the function and you integrate, then it's the function up to this boundary. So value of function in some point, at some point. Okay, and here is example. So if you take a group which is additional, so real numbers plus and plus is group operation, then left invariant form is dx, because it's a real line and coordinate is x on this real line. And if you take arbitrary g-valued form, so real valued form here, then because this group is abelian, then on commutator of this form is 0. We have a one dimension only, and Maurer-Cartan equation is d omega equal to 0. Because this omega is commutator of omega is 0, then this local condition means that there is a function from this mx to g0 such that omega is pullback of Maurer-Cartan form, but Maurer-Cartan form is dx, so it's df. So it means that if d omega is 0, then there exists some function which is differential is this omega. So it's exactly Poincare lemma. So say this Maurer-Cartan form formulation, or this Darboux derivative is exactly formulation for the Poincare lemma in the case of commutative group. So real line treated as with addition as a group. Okay, and if in addition P1 of M is trivial, so the space is contractible to the point, or the space is star shaped, then this F is globally defined, and this is the global version of the Poincare lemma. So the first one which I showed you at the beginning of my talk. So Maurer-Cartan form is non-abelian realization of the Poincare lemma. And of course, if you take this group to be non-commutative, then you have some kind of non-commutative version of the Poincare lemma. And when I saw this, I thought that that maybe it would be nice to investigate it further, but then I found a paper of some guy who did it already, so I was upset. But anyway, it's very interesting to formulate Poincare lemma for non-abelian groups, because for abelian groups it's exactly the Poincare lemma which we know already. Okay, and that's all what I wanted to say. I think it was very dense, but I wanted to present you as many connections between physics and mathematics as I know, because probably this Poincare lemma stuff is not well known by physicists or not well used to it. So it's good to know that something like this exists. Okay, so that's what I wanted to say.
Yes, it was very nice. Thank you. So I'll just stop the recording,
Okay.
and we can have a discussion. Anyone is